Hello, my name is Rania, and in this video I'll be deriving the Michaelis-Menten equation. So the Michaelis-Menten equation describes the variation of enzyme activity as a function of substrate concentration. So to start off, I'll explain the simple model of enzyme action. So the first equation I have is an enzyme E that combines with substrate S to form an ES complex with a rate constant K1 right here going forward. So now the ES complex has two possible fates. It can dissociate to ES, which is going backward, with a rate constant of K minus 1. Or it can proceed to form product P, which is the second equation, giving us a rate constant of K2. And the reason why the second equation has a single arrow is because there is not enough product P formed to make the backwards reaction more noticeable. So it's just negligible. That's why we only have a forward arrow. And to verify that this mechanism is valid, we add both of these equations together. And when we do so, we see that ES here and ES here cancel out, and the enzymes also cancel out, leaving us with S forward arrow P. And when we look at these two equations and their rate constants, K1, K minus 1, and K2, reaction K1 creates ES, and K minus 1 consumes ES, as well as K2, which also consumes ES. And all of that equals 0. And we write this as the instantaneous rate of change, which is dES over dt equals K1 times ES, E times S, minus K negative 1 times ES minus K2 times ES complex, and all that equals 0. And this equation consists of the reactants of the concentration of the reactants of K1, K minus 1, and K2. Because we have an unbounded enzyme E, therefore it's very difficult for us to determine its value. Therefore, we have another equation, which is ET, representing the total concentration of enzymes, equals E plus ES. And when we rearrange this to have E equal E total minus ES, which allows us to substitute this into our E. And when we do that, we get dES over dt equals K1 times E total minus ES, close parentheses, times S minus K minus 1 times ES minus K2 times ES, all equal to 0. Now we have to multiply K1 here and also the S to ES and ET. And when we do that, we get 0 equal K1 times E T times S minus K1 times ES times S minus K1 minus 1 times ES minus K2 times ES. And then our next step is to move all the ES complex concentration on one side. So we have K1 ES times S plus K minus 1 ES plus K2 times ES equals K1 times E total times S. And we can see that ES is the common variable among this side. So we'll bring that out. And we have ES times K1 S plus K minus 1 plus K2, close parentheses, equals K1 times E total times S. And then we divide both sides by K1 times S plus K minus 1 plus K2 on both sides. And when we do that, we get ES equals K1 times E total times S divided by K1 times S plus K minus 1 plus K2. Then we multiply this whole equation by 1 over K1 divided by 1 over K1, and we get ES equals E total times S divided by concentration of S plus K minus 1 plus K2 divided by K1. And we can therefore substitute this into another equation, which is instantaneous rate of change of the product over dt equals K2 over ES. Like I said, we can substitute this into here. And this leads us to the Michaelis-Menten equation, which we have here. V, which is velocity, is the same thing as instantaneous rate of reaction of P over dt equals K cat, which is also equal to K2 times E total times S over S plus Km, and Km equals K minus 1 plus K2 over K1. And now we can introduce Vmax, which is the maximum velocity that is attained when the catalytic sites on the enzyme are saturated with substrate. That is when ES equals E total. So we have Vmax equals K2 times E total. And we already have this right here, but it's just written differently, which is right here. Like I said, Kcat is the same as K2, so if we substitute Vmax into this right here, we get V0 equals Vmax times concentration of S over S plus Km. And that's the Michaelis-Menten equation right here.